Hi, my name is Solomon, and today I will walk you through working with some of our open source examples and ROS packages on the LoCoBot. Specifically, I will walk you through developing with Gazebo, testing out ARM poses using the MoveIt Interface GUI, and executing Python scripts with our custom Python API. You can either do this on your LoCoBot directly, or you can do a full install of the necessary ROS packages on your personal computer. For the Python API example, you will need to do a full network setup as discussed in our networking video. So let's get started with Gazebo. There are two ways you can use Gazebo. One way is to use it with MoveIt. In that case, the MoveIt launch file will load Gazebo for you. Or you can use Gazebo in a standalone fashion. In this manner, you will write your own custom code to interface with the ROS topics and services that Gazebo provides directly. So let's open up a terminal by pressing Ctrl-Alt-T and type ROS launch Interbotix XS LoCoBot Gazebo, XS LoCoBot Gazebo.launch, robot model. I'm going to use the LoCoBot PX100, but you can use whatever LoCoBot model you want. We're going to assume that there's a liner on here. All that's just going to do is just load the right links into the URDF, into the robot description parameter, so you can see it in Gazebo. There's no simulation for the sensors currently as of the timing that this video was made. So show liner is equal to true. Then use position controllers is equal to true. So this last command allows, it loads up the ROS controllers necessary to send goal joint positions to whatever joint you want to control. When MoveIt loads up Gazebo, it actually uses trajectory controllers, which allows you to send one ROS message with a complete trajectory of where you want a joint to be at given points in time. But it's not very conducive for an end user to control a joint like that. So in this case, we're going to be just commanding a goal position and having the joint go to that position directly. All right. So then we're going to also set DOF is equal to 4. By default, it is 5. So since we're using a 4 degree of freedom robot, we're going to set that to 4 and press enter. Okay, now after that loads, you want to unpause the physics engine. So open up another terminal by pressing Ctrl-Shift-T, type ROS service call, LoCoBot, actually no, not LoCoBot, type Gazebo, unpause physics, and that will start the physics engine. And let's just get a closer look here at the robot. There we go. So now I'm just going to show you the different topics that are available to you on Gazebo. So type ROS topic list. Let's just make this a little bit bigger. So the ones I want you to pay attention to are anything with command in them. So for example, the LoCoBot elbow controller command. This will allow you to send a command to the elbow joint. Or you can send a command to the shoulder controller, to the shoulder joint, or to the tilt motor that controls the movement of the camera. So let's actually do that. So we can send, let's send a command of -1 radians to the wrist angle joint. So you can definitely do this in your own custom ROS node, but you can also use a terminal command to do that. So that's the way I'm going to do it. So type ROS topic pub -1 means just to do it once. And then LoCoBot wrist angle controller command, and then just press tab a few times until you see that appear. And we're going to set it to go to -1 radians. So there is -1 radians. Now let's set the elbow to go to 1 radian. So we can just press up in the keyboard and then take out the negative and then change the controller here to just be elbow controller and then hit enter. And let's just move the waist for good measure. We're going to move it to 1 radians, 2. Actually, let's move it to 0.5. Okay, and waist controller, press enter. Okay. But you can also control the pan and tilt servos. Let's do that as well. We're gonna make the tilt, let's make the tilt servo go to 0.3. And the name of that controller is pan controller. And press enter. All right. So that's as far as moving the joints on the robot arm, or also the pan and tilt motors for the camera. But you can also move the LoCoBot base. So if you look back here, one of the topics should be for doing that. Let's see where it is. Here we go. LoCoBot mobile base commands velocity. So let's just type that in. ROS topic pub -1 LoCoBot mobile base commands velocity. Press tab a couple times. So it accepts a twist message. So this is a differential drive robot. So we can't do any movement just in the Y or Z motion here. It's also a planar robot. So we're going to set it to go to a linear translation speed of 0.3 meters per second in the X direction. And let's give it an angular component of 0.4. Then press enter. And you'll see the robot start to move around in a happy little circle. And if you want to stop that motion, you just have to give it a 0 twist, like that. Press enter, and the robot will stop. So like I said before, at the time that this video was created, while there is like some sensor feedback you can get from the camera, the transforms based on the camera that is used for the LoCoBot is not currently accurate. So that's something that will need some work. And also there is no simulation yet for the 2D laser scanner that is on the robot. But like, you know, this is an open source. This is a work in development. So it can always be improved. Okay. I think that is all you need to see for the Gazebo environment. It's really all about creating a ROS node that publishes to these topics that I told you about, and that should help you get started simulating. So Control C out of that. Might take a few seconds. There we go. So the next demo I want to talk about is the MoveIt Interface GUI. So this is a ROS package that I created that builds on top of MoveIt. It takes advantage of the MoveIt, the Move Group C++ API that MoveIt offers. So I have a ROS node with a very simple class that wraps around the Move Group C++ API that allows you to plan motion and execute motion. And then on top of that, I created a graphical user interface using PyQt that allows you to input specific poses that you want the arm to go to. And then that sends the commands to the little ROS node that I created that wraps around the Move Group C++ API and will make the arm move. So let's start that up. We're going to be using a fake arm just because. So let's type ROS launch Interbotix XS LoCoBot MoveIt Interface XS LoCoBot MoveIt Interface.launch robot model. We're going to use the 6 degree of freedom here. LoCoBot WX250S. Of course, you can use whichever arm you want. Show LiDAR. Let's just set that to true, just for collision detection purposes. Though why the arm would ever be in a place where it would collide with the liner probably would never happen, but just for the sake of accuracy, we're going to set that to true. Use fake is equal to true as well. That just means we're going to use MoveIt's. They have a fake plugin that allows you to simulate a fake robot in RViz if you don't have access to a physical robot or you want to try something out on a virtual robot since you're not sure how the arm will react. So set that to true, and then we're going to set degrees of freedom is equal to 6 since we're using a 6 degree of freedom arm. By default, that is set to 5. And then we want to set use CPP interface is also equal to true. Like I said, this GUI, it publishes commands to a small ROS wrapper that I wrote. That's in C++. So that's where that name comes from. And let's type enter. So here we go. You might notice some warnings appear, like specifically this warning. Failed to find 3D sensor plugin parameters for Octomap generation. That's actually a very well-known issue with MoveIt. But it doesn't affect the usage at all of MoveIt, so nothing to worry about. And this warning here, RViz Visual Tools unable to connect to any subscribers within half a second. You don't have to worry about that either. It's just a matter of when certain parts of the software are loading. So when I think here RViz is trying to connect to a topic, but it's not there yet. But the topic will eventually be published to once that node starts. All right, so here we have our Widow X250 6 degree of freedom LoCoBot, and we have our GUI. So something to note before we go on here is that the reference frame for planning is LoCoBot base footprint, not the ARM SpaceLink frame. So the ARM SpaceLink frame is like over here at the base of this cylindrical base of the robot. Whereas the base link frame of the robot, the base footprint frame of the robot is like at ground level right in the center here, like right over there. So that's just something to keep in mind when you're sending commands. And you can actually figure out what that transform is. You open up a terminal and you can type ROS run tf echo LoCoBot base footprint, and then LoCoBot ARM base link, press enter. So that just tells you that the ARM SpaceLink frame is pretty much around 0.1 meters along the X direction and 0.1 meters in the Z direction. So that's just something to keep in mind, like I said before. Okay. Anything else to talk about? So the main purpose of this GUI is so that you can test out poses to see if they are valid, and you can visualize where the arm will end up before putting that desired goal pose in your own code. Maybe you want to build a certain number of, you want the arm to follow some waypoints, and you want to figure out if those waypoints are valid before you input it into your code. So this would be a great tool to use to see if they are even valid. So let's just walk through the different aspects of this GUI. So the XYZ here, you specify your desired goal pose position, in meters, and then your roll, pitch, and yaw, you specify your desired orientation in radians. Plan pose, so that button sends a command to MoveIt to tell it to figure out if it can find the right joint positions needed to get the arm to its goal pose. So let's just try that out. Here we go. So let's just set X to 0.3 meters, and let's set Z to 0.3 meters, and let's just set Y to 0.2 meters, and let's just keep the orientation constant. Actually, no, let's not. Let's change the pitch here to 0.1 And then we can press plan pose. So it's able to figure that out. You can see here there's a message that says planning EE pose was successful. And then you can actually execute it and the arm will actually move there. So that is great. So that's what the plan pose does. What the plan position button does is it essentially allows you to specify an XYZ position. And no matter what the orientation is, like you can press the plan position button and it'll just try to figure out a valid arm position that will get the end effector to the XYZ position, regardless of what the roll, pitch, and yaw is. Plan orientation does the exact opposite. If you tell it what your desired orientation is, it'll try to figure out a goal pose for the end effector that will achieve that roll, pitch, and yaw, irrespective of what the actual X, Y, and Z positions are. There really isn't any reason to use the plan orientation button. It just kind of included it there for symmetry purposes. But, you know, you can plan, yeah, like you can press a plan position there, then execute it. It'll do this funky kind of motion, whatever, but the end effector will end up in the right spot, just the orientation will be totally random. And if we do it again, it might do a different, there we go, it might do a different orientation. And I bet if we press plan orientation, oh, there we go. It'll achieve 0.1 radians per pitch and 0 for roll and yaw, but, you know, it doesn't really help anyone if you don't know where the end effector is going to end up. But, you know, something you can do if you want to. Then something else to note is that if you try to send a command that is obviously not possible, so let's say you say you want your X to be like 0.7, and then you try to plan a pose. Well, actually that is reachable, so hold on. Let's change the height here to 0.5. Plan pose. There we go. So that's a little bit too far out of reach. So you'll see this message appearing saying it's planning, but then eventually it'll figure out that it can't find a valid solution, and it'll tell you that planning EE pose was not successful. So since this is a 6 degree of freedom arm, more likely than not, you'll always find a valid solution. But for our 5 degree of freedom arm, or 4 degree of freedom arm that comes with the LoCoBot, there will be times when MoveIt will not be able to come up with a valid solution. And even it might be possible, but MoveIt is mostly guaranteed to work with 6 degree of freedom arms or more. It doesn't really work as well with 5 degree of freedom arms or 4 degree of freedom arms. So there's a higher probability that it won't find a valid solution for lower than 6 degree of freedom arm cases. Okay. So that is that demo. Let's go on to the Python API. So Control C out of that. And let's start the Python API code. So for this example, I'm going to work with the physical robot. So I have to SSH into the LoCoBot. I am currently connected to a different network. So I'm going to select network. Okay, we want to go to LoCoBot hotspot. So connect to that, LoCoBot I hotspot. All right. I'm just going to exit out of this and open up a fresh terminal. Now let's SSH into the LoCoBot. SSH LoCoBot at locobot.i.local. Again, the reason I'm using LoCoBot I here is because there's lots of different LoCoBots in the office, and in order to make sure I'm connecting to the right one, I temporarily changed the host name for my LoCoBot to LoCoBot I. But in your case, you will always be SSHing into LoCoBot at locobot.local. So press enter, type yes, password is LoCoBot, all lowercase, and you should be in. So let's type, let's get the launch file started to use our Python script. And what this Python script will do is actually move the arm, move the pan tilt servos, and actually move the base. So just a combination of different things to show you what the LoCoBot can do. So let's type ROS launch Interbotix XS LoCoBot control XS LoCoBot Python.launch robot model. I'm using a LoCoBot WX200. But if you're using a different robot, you would put the model there. useNav is equal to true. That just tells it we're going to be doing navigation, which is true. Part of the script will involve moving the robot base. Use LiDAR. Let's tell it to use the LiDAR, the onboard LiDAR that I have with the Widow X200 LoCoBot. And then we're going to start a new map from scratch. So we'll be doing SLAM here. And, RTAB map args-d and press enter. Okay. So that started. Now press Control-Shift-T. Now we have to make sure that our terminal has the right ROS master URI variable set. So let's just edit that very quickly. nano.bashrc. Go all the way to the bottom. If you don't have this command in here, you should stick it in there. Just exports the ROS master URI variable to be the one for your LoCoBot computer. Like I mentioned, mine is called LoCoBot I, so that's what it's called. So press Control-O, enter, and then press Control-X. And then if you were to check your environment variables right now, you would see that it hasn't changed. It's still localhost. So in order to make those changes take effect, you have to source your workspace, or source the bashrc file. So that's what I'm doing here. Now, if we type that command again, you'll see that our ROS master URI is now updated, which is great. So let's type ROS launch. We're gonna monitor the state of the LoCoBot in Arvis. So Interbotix XS LoCoBot descriptions, remote view.launch, Arvis frame is equal to map. Press enter. And let us click the move base toggle and the map display. So this shows you the robot doing SLAM already. And now we're going to run the Python script. So I'm going to actually run the Python script on my personal laptop. But like I said, you have to have all the ROS packages installed on your personal computer to do this. So cd Interbotix workspace, source, Interbotix ROS, rovers, access LoCoBots, examples, Python demos. So the one I'm going to be doing is called combo control. So you can see it in the terminal here. But something that's very important is that you will have to change your robot model here to be the robot model that you're currently using. Mine's already set to Widow X200, but that's something you're going to have to change. Press Q to get out of that, and then we're going to run it. So Python combo control.py. Enter. So you can see in Arvis here what the robot is doing. This is a modified version of the bartender script that you might be familiar with our standalone arms. So that's the first thing that it's doing. And then after it does the bartender script, it's going to move the base to a 1 meter in the X direction and 1 meter in the Y direction relative to where it currently is, like you see over here. The green line represents the global pose, the global plan, and the red line represents the local plan. So I think I tell it to go to 1 meter in the X and 1 meter in the Y, and also have 3.14 radians for orientation. And then right after it finishes that goal pose, I tell it to go back to 0, 0 with an orientation of 0 as well. So essentially back to where it started. And afterwards, I think it's called, it does the EE Cartesian trajectory script, where it essentially draws us a square in space with the end effector of the arm. Then it pan and tilts the camera servos before bringing it back to its home positions. And that's the end of that. You can see the actual code here. So this block of code is responsible for like the first part. That's more of the bartender script. This is for moving the base to a goal pose of 1 meter in the X direction, 1 meter in the Y direction with an orientation of 3.14. And then it moves it back to 0, 0 with an orientation of 0. And then finally it makes the arm draw a square using a square-like trajectory in 3D space. Then it pan and tilts the servos, and the script ends. Okay, so that covers this tutorial. Hope you enjoyed it, and I will see you next time.